Okay, so we started studying polynomials over fields. Right, so polynomial has monomials in X, coefficients, and coefficient and monomial together they are called terms. Monomials are just product of variables. In our case, we'll not have time to study anything about multivariate, we'll just work with single X. So these are the example polynomial rings, Qx, Rx, Cx, Fpx, and you can add and multiply in these rings, polynomial rings. We define degree, which is additive on multiplication, and on addition it is you only get a upper bound. The degree on addition can fall all the way to minus infinity. And then we did division, which is long division of polynomials. So it gives you a unique remainder. And based on, so once you can do division, then you can define GCD and Euclid GCD and all these things that and we'll also study factors and unique factorization. So we can repeat the things that were done for in the case of numbers. Any questions? Okay, so we saw here that GCD, I mean, we have to talk about monic also, otherwise there will be infinitely many GCDs. Right, so for 2x, 4x, there are many GCDs, but monic one is unique. So that is GCD X. Then we have this observation that we had for numbers, that if you can write after division f equal to qg plus r, then what is the GCD of f and g? What was the first step in Euclid GCD algorithm? Yes, so you write f as qg plus r, and then g part you can drop, so you get g comma r. So this was the first step in Euclid GCD, and you can do the same thing now with polynomials. So in the recursive call, what is the parameter which will reduce? In the case of numbers, it was their size. Here it will be degree, right? So degree falls. So based on that, you have an algorithm, finite algorithm, because now you will divide g by r. Degree will further reduce and keep on doing this. So in very few steps, you will reach the GCD. So just to recall that, so let the degree of f be greater than or equal to degree of g. Then degree of r is strictly less than degree of g, which is less than or equal to degree of f. So from fg you move to g comma r, so that's a smaller instance, and then continue this process. To get like Euclid. F equal to q1 g plus r1, then you will have right, and so on. So in the end you will get so we want Rn minus 1 . So this is second quotient, get a quotient here n minus 1 plus Rn . And the last, so this is happening how many times? N times, right? So Qn. So what can you say in the end? What is this Rn? In the end, the remainder will be a constant. So it can be 0 or 1. Right? If it is 0, then you say that the GCD is, what do you think? So Rn equal to 0 implies that the GCD is Rn minus 1. Otherwise, what happens if Rn is 1, which means, I mean, Rn can be any non-zero constant, so we can take it to be 1 also. Actually, can we take it 1? I don't think we can always take it 1. Let's keep it separate. So it's an element in F. It's a field element. So if Rn is not 0, so it's in F star. Then what can you say about the GCD? Yeah, the GCD, so the F and G are co-prime. So the only monic factor that's common is 1. Is that clear? So you keep reducing the degree of the remainder, ultimately degree becomes 0, which means it's a constant. So if it's a non-zero constant, then you say that, then you know that F and G are co-prime. If it's 0, so basically this is the remainder which is of degree minus infinity. That's the good case, or it's the case where you get actually a GCD. Rn minus 1 is a monic polynomial of degree positive. What can you say about the number of steps in this algorithm? So this number of steps n is at most what? Degree of f. So if you, I mean, this algorithm will be fast in terms of the input, right? So as big your polynomial is, input polynomial is, that many steps and not more. So this is what you would consider a very fast algorithm. It's a linear time algorithm, almost linear time. In one step, it is only doing division. Right? So assuming that division is fast, this is a very fast algorithm to compute GCD. Is this clear? So you can check the GCD of x plus 1 and x cube plus 1 through this. So you divide x cube plus 1 by x plus 1, immediately you will get a remainder which is constant equal to 0, right? So you will get that the GCD is x plus 1. So this you can check. I mean, to check this, it's very easy. You can just substitute in x cube plus 1 minus 1. You see that it's 0. So x plus 1 is a factor. Right? So R1 already is 0. Right. So the point of this writing these equations down was that now you can do what you did with numbers. So you can substitute the second equation in the first equation, and then followed by third equation in the previous equation, and so on. So that will give you the following identity called the Bezout identity. Which is that EF plus BG is equal to the GCD of F and G. Right, so this will give you polynomials AX and BX such that the combination of F and G with that is exactly equal to GCD. So when GCD is 1, this is a bit surprising that F and G are big polynomials, but you can still combine them and get the answer 1. Right, so you can prove this as an exercise. And is this Bezout identity unique? It's not unique, but I can make it unique by saying that degree of AX is less than G and B is less than F. So there exists unique AB such that degree of A is less than degree of G and degree of B is less than degree of F. Right, this also you can prove as we did in the case of numbers. There we had to worry about this sign, etc. Number can be negative also, positive also. But here it will be cleaner. Here it is just the degree which is which can only be greater than or equal to 0. So as long as A and B satisfy this, you have a unique AB. Right? The proof idea is again that if A has degree G or more, then you just divide it by G and reshuffle this identity. Is that clear? So proof will just be that observation. That any you can subtract from A anything U times G, and how will B change? UF. So that's all. So which allows you to divide A by G and get to the remainder. So A will be replaced by something small, and you can show that this B plus UF will also be small, because their combination has to be F comma G, which is small. So finish this proof. It will help you understand the definitions that you have seen till now. Yeah, so any questions till now? So next thing we can do is we can define prime numbers in this ring. So what are the primes in this ring? What should be the definition? Yeah, so irreducible polynomials. So what is a reducible polynomial? So a polynomial is called reducible if f is equal to gh for such that degree of these GIs is smaller than degree of F, and also it should be positive. Okay, so in this case G1 is a non-trivial factor of F, and so is G2. So this is a non-trivial factorization. So if there is a non-trivial factorization, then we call F to be reducible. And if this doesn't happen, we call F irreducible. Okay, so this is the definition of primes. It's called irreducible or prime in the polynomial ring. Is this clear? What about x square? X square is reducible, right? What about x square plus 1 over reals? Yeah, because the only way this can factor, is x minus square root of minus 1. Right, but this is these are not in the real field. So you learn two things. One is that it's reducible over complex. But it's irreducible over reals and rationals, right? So same polynomial may have different behavior if you change the field. This is what much of algebra tries to study. As you go to different fields, what happens? Okay, and what about x square minus 1? This always factors, right? Is always reducible. What about x plus 1? So all linear polynomials, degree 1 polynomials, they are by definition irreducible. They are irreducible. Over all fields. Okay, linear polynomials have no way to give G1, G2 of degree each at least 1. Okay, so they are always irreducible. And so are constants, but constants aren't interesting. So we are interested only in these positive degree polynomials. Okay, so let's prove a quick property. So F is irreducible. Then what is the GCD of F and an arbitrary polynomial G? Sorry? Yes, so one can always happen because G is arbitrary. But the only other option is if GCD is H, then H has to divide F. Right, but the only way that it can divide F is if it is F. So 1 or F. Right, so this is an important property of irreducibles. It follows directly from the definition. This is why it is exactly as primes in numbers. So GCD has only two options for irreducible. Otherwise, of course, this is not true if F was reducible. Okay, so now let's talk about factorization. So given a polynomial F in the polynomial ring, if F is reducible, then you can write it like G1 times something else. So find a factor, both are non-trivial factors, right? They will exist. So if F is irreducible, then you stop, then there is no need for further factorization. But if F is reducible, then you can factor it, and then you can move to the factors. So if GI is reducible, then further factor. Now, since I have not told you how to factor, I mean, I haven't given you an algorithm for factorization, but this is just a thought experiment. So if there is a way to factor any of the factor, then you continue that. Otherwise, you don't do anything, right? So when you do this for several steps, ultimately you would have written F as a product of irreducibles. Is that clear? And in fact, I can throw in a constant here and make this monic. C is in F. Okay, so you can make, basically factorize F into irreducible factors in finitely many steps. Is this clear? Number of these GIs will only be finite, because when you factor, the degree falls. Right, so we have shown that there is always a factorization into monic irreducibles. That is what we have shown in this thought experiment. Okay, now can you show that this factorization is unique? Like for integers, it is unique into primes. In this ring, in the polynomial ring, is it unique? What is the proof? So let's prove that. So factorization of F into monic irreducibles is unique, obviously up to ordering of these polynomials. So of course you can swap G1 with G2, the order will not change the product value, but other than that you cannot do anything. The set of GIs and the set of corresponding EIs, that is unique once you have an F. Okay, so here also we have the same property as we have for integers, which is unique factorization. So both these rings are unique factorization rings. So proof of this you have already seen, it's the same proof as in integers. So you write F as in two ways, so GI, EI and HI, EI prime. I mean, there is also a constant in both these terms, actually we can put that. In general, this is the factorization. There is a constant multiplied by sequence of powers of irreducible polynomials which are monic, and they are degree 1 or more. GIs are not constant. So this degree is positive. So then what happens is, what can you say about C and C prime? Why are they equal? Because this is the leading coefficient of F. So the leading coefficient of F is on one side it's C, on the other side it's C prime. So both are equal. Right? That is the proof. Look at the leading monomial which is being produced in a product. That is being multiplied by C, respectively C prime. So we can get rid of C altogether and we can now study the two products. So now what? So at this point we need the cancellation claim that we had in integers, which is that if G and H are co-prime and G divides H times V, then it means that G divides H or V? G divides V. Right? What was the proof of this? Bezout identity was the proof. So you write AG plus BH equal to 1, then you multiply by V. And now since you are given G divides HV, so G divides the left hand side, so G divides V. Right? So this nice proof comes because of Bezout identity, because of Euclid, extended Euclid algorithm. And yeah, you just repeatedly use this observation. So if G1 and H1 are co-prime, then G1 has to divide the remaining HIs. So somewhere then G1 has to overlap with HIs in the end. So apply this repeatedly in equation 1. for let us say G1. So then what you get is that there exists some I1 such that G1 and HI1 are the same. Okay, so what happens when G1 and HI1 are the same? Say G1 is equal to H1. What can you say about E1 and E1 prime? By the same argument, they will also be the same. Okay, and you keep doing this. So ultimately you will get that the set of G1, okay, what you will get is there is a permutation pi such that G1 is equal to H pi 1 and E1 is equal to E prime pi 1. Is that clear? So that is the only thing which can be changed in the factorization, the ordering. Other than the ordering, basically the prime powers, they are equal. Is that clear? So that gives you a unique factorization in fx. Sorry? Well, because on one side you may have G1 times G2 and on the other side you may have G2 times G1. That is all this is saying. It's of very little consequence, but to write down the proof, you have to say that G1 is equal to some Hi. Right? So how do you say that? You say that G1 is equal to Hi1 and then you cancel both these, cancel from both sides and reduce to a smaller problem of searching for G2, then for G3 and so on. Any other question? There is this small observation that you can prove. So if fx is a polynomial and you have a linear polynomial x minus a, what can you say about the GCD? When does a linear polynomial share a factor with an arbitrary polynomial? So yes, so it will be x minus a. The case when x minus a divides. So in this case, x minus a is irreducible, right? So GCD will either be 1 or x minus a. So it is x minus a if f of a is 0, and it will be 1 if it is not 0. Right? So this you can easily prove. This is the proof is simply by long division. You see that in the long division, in the end, the remainder that you get is fa. The polynomial basically, so long division basically evaluates the polynomial f at a. That's the remainder, right? So if the remainder is 0, then you have a GCD, otherwise you have 1. So such A's we obviously call them roots. It's a root of A, root of F. If f of A is 0 for A in the field, then we call A root of F. Okay, so this A is called a root of F. now let's go back to what we had shown, this unique factorization, or even in fact the factorization. Looking at this factorization, what can you say about the number of roots of f? How many roots can f have? Can it have, so if the degree of f is d, can it have d plus 1 roots? Why not? Sorry? No. Maybe there are two different products. Yeah, so then you also need unique factorization. So because there is only one factorization, yeah, and then you are correct that in one factorization there can only be d factors or less. So there cannot be more than d roots. So that's another major property of polynomials. It's used a lot in computer science. In fact, it's a corollary of that theorem. So number of roots of f in f is less than equal to degree of f. So proof is let alpha 1 to alpha r in f be distinct roots of f so then what you can write is fx is some x minus alpha 1 e1 x minus alpha r er and a remaining cofactor which may also be 1, or it is some other polynomial which does not have roots, it is free of roots. Right, and from this you deduce that, so this was uniquely so there cannot be any other way to get roots, right? Alpha 1 to alpha r which appear in this factorization is the only possibility, and clearly now comparing by degree you will get that degree of f is greater than or equal to r. Is this clear? So you get a bound on the number of roots. I think this was already needed in some assignment 3 question. But there we will not ask you to give a proof. But once you have shown unique factorization in the polynomial ring, you get this immediately. So if the field is complex field, how many roots will you get? Yeah, so there are fields where the number of roots is exactly degree, right? Are there fields or polynomials where the number of roots is less than the degree? Yeah, sure. For example, you saw x square plus 1. Right, this x square plus 1 factorization over complex it gives you 2 roots, over reals it gives you 0 roots. So this may be an inequality. Usually it's much smaller than degree of f. Okay, so yeah, any questions at this point? If not, then we will go deeper into the field structure, and there you will need these ideas. You need to understand them better. So next what we will show is the cyclic structure of finite fields. Okay, let me not put star already. So if you look at Fp plus, the additive part, is there a single element which can generate all the elements by addition? One, is there any other element? Everything will work except 0. For all, well, so 1 is clear. So if you keep adding 1 to itself, then you get all the elements. And for any element in Fp star, which is, by Fp star I will mean Fp minus 0. So for any element, A generates under addition. Okay, this is a fairly simple property. And it is true for this finite field, this prime field. For other fields, it's not true. So now what we want to show is that something good happens with multiplication also. So what about Fp star under multiplication? So under multiplication, you know that this set is closed, right? In Fp star, not just closed, but in Fp star, you multiply 2 elements, you get a third element in the same set, and any element you can also take inverse. So focus on this set. Now, is there an element A in this set which under multiplication with itself can generate everything? Right, so if you took 1, then 1 times 1 will be just 1, so 1 is completely useless. If you take 2, then you have to look at powers of 2. So for example, can powers of 2 generate all the numbers mod p, except 0 of course? How do you say no? That confidence has no basis. No, this is p. This is a general p. So for any p, for prime p, yeah, so the thing is, you can look at powers of 2, powers of 3 and so on, but then there is no basis. It's not clear what will happen for a given prime p. For prime p, 2 may work, but then for other primes p, 2 may not work. When 2 doesn't work, then what will work? So it seems to be a very complicated problem to identify which elements will generate the powers of an element A. So that is what we will resolve in this class. So such a magical element is called primitive element. Yes. Sure. Yeah, but then you are adding powers. Here the operation is multiplication. So here you have to look at A and then A square a cube dot dot e to the p minus 1. That's the question. This set, is this equal to fp star? Does there exist an A? Such that the set of all the powers, and this is obviously we are working mod p, it's not that we are looking at a cube, you do a cube and then you reduce mod p, and then you will have numbers 0 to 1 to p minus 1, but are all of them represented? Are they present in the set? Is there such any? That's the question. So for the binary representation will not help at all because there is no addition happening. Addition was in the first part when we looked at 1 plus 1 plus 1. That was the easy part. This is the harder part. So here, if A generates or powers of A, let's say, fp star, then we call it a primitive element in fp. Okay, so in a prime field, primitive element is an element whose powers will give you any number you want except 0. Powers cannot give you 0, so you just exclude that. So question is whether primitive elements exist. So we will show that they exist, and in fact we will also count them, and we will also give you an algorithm to find them. Okay, we will solve this thing completely because these things are needed in practical applications all the time. But before that, we have to give you more definitions. So since you are interested in powers, so we want to first understand for any A, can you show that that this set contains 1? That's the first question. Sorry? A to the p minus 1 contains 1, okay. That was easy. Can it contain 1 before p minus 1, a to the p minus 1? So wherever the first place 1 appears, we call it the order of A. So for A in FP, order of A, let's say E, is the smallest number such that A to the E is 1. It's also, we need positive. Obviously, E equal to 0 will always work, but that was your p minus 1 kind of. So we don't want A to the 0, we want something more interesting. So for an A, we define E to be the smallest positive number such that A to the E is 1, and you can show that E is positive and it's smaller than p minus 1. Is it, well, less than equal to? Okay, because E equal to p minus 1 certainly satisfies this. So the correct answer will be between 1 and p minus 1. Is that clear? Yeah, so for every element you have order, and I should actually say except 0, A is in FP star. We are not interested in 0 in this. So do we have examples? So what is the order of 2 in let's say F3? Yeah, so 2 is minus 1 square is the first time you get 1, right? So this is 2. What is order of 2 in F5? That's 4. In F7? So 2, then 2 square is 4, and then 2 cube is 8, which is 1, right? So this is 3. So as people had guessed that 2 will work, their guess is correct for F3 and F5, right? Because for F3 star, 2 gives everything, for F5 star, 2 gives everything. But for F7 star, it dies in the middle, right? So it goes only 2, 2 square, 2 cube. After that, 2 to the 4 is the cycle repeats. So 2 is not a primitive element here. So here it is primitive, but here it is not primitive, so imprimitive. Right, so the same number as you change p, same A, as you change p may become primitive or imprimitive. Right, that's not easy to predict. That's a hard property actually. It's kind of a random behavior, so you don't know how A will behave as you change P. Okay. Yeah, so let's prove some simple properties of order. So if order of A is E, then show that let's take, let's call P minus 1 n. So then that is not what I want, sorry. Order is this in some prime field. Then for any number n, if A to the n is 1, yeah, so let's read this. So order of A is E in the prime field, and suppose somebody gives you another n such that A raised to n is 1. What can you say is the relationship between E and n? Sorry? Can you say n equal to E? No, you cannot say n equal to E because yeah, n can be 0 or n can be 2E. So what you can say is E divides n. Okay, so a to the n is 1 only for multiples of the order. It's if and only if. Let's prove this property to warm up your definition of order. So, so let us divide n by e. Let us divide n by e and r be the remainder. So, it is between 0 and e minus 1. So, a raised to n equal to 1 implies that a raised to qe times a raised to r is 1, which implies what? Well, a raised to qe is 1, so a raised to r is 1, which implies what? Now remember that e was the least by definition, but now you are getting a raised to r equal to 1 where r is smaller, so it means that r is 0. Right, so we have shown that e divides n. And what about the other side? If e divides n, then a raised to n is, well, you can write it like a raised to e raised to n by e, which is 1 to the n by e, which is 1. Is that clear? So now we have an understanding about when does a potentially not work. It will not be a primitive element, right? So it will not be a primitive element when its order is smaller than numbers you want, smaller than p minus 1. But when that happens, e will be what? What will be the relationship between e and p minus 1? Yeah, so we have shown that e divides p minus 1. That's the immediate conclusion, that order of any element divides p minus 1. Right, so the proof of this is simply that well, a to the e is 1 and a to the p minus 1 is 1. So which means from the previous observation that e divides p minus 1. Is that clear? So when e doesn't work as a primitive element, then it means that it reached 1 before, and after that it's just copies of the same values. Any questions? Okay, one more property we need, which is what can you say about the, okay, let's keep the notation. So E is the order of A in FP. And K is a natural number. Then the order of A to the K is what? If you know order of A, then what can you say about the order of A to the K for arbitrary K? Like what is order of A square? Well, clearly A to the 2e is 1, but is 2e the order? So if E is even, then E by 2, oh sorry, E to the 2e is 1, but E may not be the order of A square. E by 2 may also work, right? If E is even, then E by 2 will work. And if E is odd, then E will be the order. So what you will get in general is E divided by the GCD of E and K. Okay. So when K is co-prime to E to the order, then the order doesn't change. But if it shares a factor, then you can save on that GCD. So how do you show this? Well, first you can observe that this number E prime, what is A to the K to the E prime? So this is Ke divided by E comma GCD of E and K, which you can also write as this. Right, so here instead of K, I am now looking at A to the E, and outside you have a number because GCD of EK obviously divides K. So this is 1. Right, so E prime certainly makes A to the K 1, but is it the least? That's all you have to now check. Yeah, so that needs to be checked carefully. So suppose A to the KL is 1. So now you have the property that if A to the something is 1, then order divides it, right? So it means that E divides what? KL. If E divides KL, I want to remove K from this equation. Can you do that? By the GCD, right? So let's do that. So E by GCD, that's actually E prime. So E prime divides K by GCD times L. Right? That's equivalent because we have on both sides we have divided by the same thing. Now what? So now notice that E prime and this thing, they are co-prime. Right? Because the GCD has been removed from E and K. So if you remove GCD, then they are what is left is 1. I mean the GCD then is 1. So what can you reduce from this? That then E prime is forced to divide L. So E prime is the least. So the two overall give you that order of A to the K is E prime. Okay.